Good morning, everyone, and welcome to Year 11 Physics. May I start today's lesson with an apology? I've been editing yesterday's lesson, and my goodness, that was awful. It was me standing here talking with a stack of equations on the board. I am sorry. However, had to be done. So, going to do a little bit more today, and then you're going to do exercises from the STARWA, which I've scanned and put up onto yesterday's lesson for you. But what I realized in yesterday's lesson was I went straight to the conservation of momentum, and I probably should have given you a couple of ideas about momentum to start with today. So just a couple of grounding ideas to do with momentum. One, that it is the tendency for something to continue in its line of motion, okay? So momentum is the tendency for an object to continue in uniform motion. We know what uniform motion means. It means to continue in the same direction at the same speed. So that's number one. This is what it is. Two, mass is important. I won't say it. I won't say mass matters, but it does. Mass is important. Velocity is important. Heavy objects with small velocities have lots of momentum. Small objects with high velocities have lots of momentum. Heavy objects with high velocities have lots of momentum. So mathematically, we have momentum is equal to mass times velocity, or rho is equal to mv. That is the Greek letter rho. It is not a P. It's a rho. You will see in some textbooks they'll have it as a P just because they can't get the rho to happen with their editor. The units of momentum are kilograms meters per second. They're the units of momentum. So when we're mucking around with momentum and we've got our equation going, you will see us saying that momentum is equal to mv, but sometimes you see us use the expression mu. Always in Year 11 physics, when we're talking about momentum, we are talking about an interaction, a change in momentum is what we're usually really interested in. So there's the before and the after. So that's why we will talk about the difference between initial velocity versus final velocity. These things are important. We will be mucking around with those as we go through. Initial velocity and final velocity. Momentum is conserved. Momentum is conserved. If two objects interact with each other, the momentum they have before the interaction, the momentum they have after the interaction is the same as a sum total. Momentum before is the same as the sum total as the momentum after. And we saw that yesterday when we were mucking around with the trolleys. We had a bit of an intuitive sense of it. One trolley comes in, it hits the other trolley elastically with the springs. The other trolley moves out at the same velocity whilst the original one becomes stationary. If you have one trolley coming in and it strikes a stacked double trolley, then there's a different activity again. So the momentum before must be equal to the momentum after. The momentum of any individual body can change, yes, but the momentum of a system must always remain the same before and after an interaction. What that means mathematically is the sum of your momentum's initial before the interaction must equal the sum of your momentum's after the reaction, final. Before must equal after. The individual parts can share momentum, swap momentum, exchange momentum, but if you tally them all up before and tally them all up after, they will be the same. This is easy to see with trolleys. If you're playing a game of pool or billiards and you go to crack the triangle. Do you know what I mean by the triangle? You set up the balls in a game of pool. You got all the balls together. If you send that cue ball down towards your triangle of balls, that cue ball will have momentum. That is your before. Once it cracks the set up balls, they go scattering everywhere. You add up the individual sums of all of those balls plus the cue ball, it will add to the same momentum as what the cue ball had before the interaction. When you do calculations in momentum, when you do calculations in momentum, always make sure you have yourself a diagram, that the diagram has an orientation. You might say to the left is negative, to the right is positive on your diagram. Make sure that you remember conservation law is the secret to answering all of them. So that which is before equals that which is after. Declare the equations. Make sure you keep track of what's positive and what's negative. Show all your working, give your answer. Don't forget the units, kilograms, meters per second. The best thing you can do now is just have a go. I'm going to have a go at a few problems on the board. I will record myself doing it. You don't have to pay attention to me. What you will do now is go to our sector lesson, download Exploring Physics problem set that I've left in today's lesson, and have a bit of a go at it. That's what you've got to do right now. Get into it, guys. So when we go to understand impulse, we're interested in Newton's second law of motion, force equals mass times acceleration. And we remember that acceleration is defined as change in velocity on time. Change in velocity on time, which equals v minus u over t. So if we take this and we bring it over here and swap out that a, what do we end up with? So our Newton's second law becomes force equals ma, where a is v minus u on t. Multiply the t over to the ft. We end up with ft equals mv minus u. Ft equals mv minus mu. Mv, that's the final momentum. Mu, that's the initial momentum. So ft is equal to the change in momentum of a body. So when we're talking about this impulse here, we're focused on one body. We're trying to examine what happens to that body in an interaction. So we're not talking about a system. We're talking about one body only. So the momentum in a whole system must be conserved, but the momentum on one body does not have to be conserved. Now, this F multiplied by T, we call this impulse. If you want to change the momentum of an object, then you apply a force for a period of a time. You can apply a very large force for a small amount of time. You can apply a very small force for a large amount of time. And the example we always give, if I want to move my car down the street and get it up to 36 kilometers an hour, am I personally strong enough to do that? Well, yes, I am. Yes, I am. As long as I can keep pushing that car with whatever force I've got, if I can keep pushing that car for a long enough period of time with the same force, I will eventually get it up to 36 kilometers an hour. Of course, for me to actually do that at 36 kilometers an hour, I'd have to be sprinting behind that car by the end of the story, because 36 kilometers an hour is 10 meters a second, which is Usain Bolt fast. So I'd have to actually apply my best force to the car as the car gets faster and faster and faster. Now, it's easy to apply your greatest force to something that's stationary, but if it's moving away from you, then it gets harder and harder and harder to apply your maximum force to that body as you're going and moving faster and faster and faster. So this is impulse, and you'll be using it in the questions in this next set. Okay, good luck with that.